Okay, thanks a lot, Omkar, and thanks for having me here. So these are really supposed to be lectures, and one thing that shows that is most of the papers that I'll be talking are about now 3 years old or 2 to 3 years old. So there will not be much new in these lectures, but I hope to convey to you the importance of this subject and the fact that D-instantons are an important physical thing in string theory, and that string field theory plays a very important role in understanding the effects that they have. So first we'll start without D-instantons. So like the first question is, why do you need string field theory? Okay, so why do you even need it? Because textbooks tell you that if you have string theory in flat space, then the basic observable is the scattering amplitude, and the scattering amplitude can be written as just a moduli space integral. And people say there are no UV divergences, so you are done. So that's it. So string field theory gives you the amplitudes as a finite integral, and you go home. Okay. So but let me write the first formula. So there is this thing. So there's dx x to the minus s minus 1 minus x to the minus u minus 1. Okay. So can anyone tell me what this formula is trying to compute? Yeah. Maybe some of the students, have you seen this? Yeah, it's the Euler beta function, but in the what is it a scattering of?
4-point
open string. Okay. So this is a 4-point gluon amplitude. So we have 4 gluons. Okay. Clearly did not draw this right, and it's tree level. So okay. And let's imagine that you have particle 1 plus particle 2 going to particle 3 plus particle 4, and then the Mandelstam S is negative P1 plus P2 square, and that's positive because they are incoming particles, and this is positive. Okay, so you already see a problem. The fact that S is positive means that this power of x has minus something bigger than 1. So it's minus 1.1 minus 1.2, which means this integral does not converge near x equal to 0. So it's actually divergent. So even though people write down the beta function, the simplest expression in the physical kinematics is actually divergent. The other factor is fine because u being negative p1 plus p4 square is negative. So you don't have problem from that, but this is really divergent. Okay, and I should say that just for context, this is some, let's say, to be concrete, the tachyons are not playing a role here. So this formula is for type 1 string in 10 dimensions. So you have Minkowski space 10D, it's type 1, so that means there are 16 supercharges. And in this background, there are 32 D branes, which give rise to an SO32 gauge fields. Okay, and no tachyons. So this formula is not diverging due to tachyons or anything. This is in a tachyon-free supersymmetric theory that you have this divergence. This is a scattering amplitude of 4 gluons of these gauge fields. So in the background, there's not just flat space. There are 32 D branes that are needed. So there are gauge fields that have SO32 gauge group. So you have gluons of those SO32 gauge fields. And actually, this is one particular color ordering. So what we are computing is that there would be some gauge group indices here, 1, 2, 3, 4. And this particular term, this thing with kinematics, is not the full amplitude. It will multiply something like trace of TA1, TA2, TA3, TA4, and also some polynomial in momenta and polarizations, right? So there is all this stuff that I have not written, but the main sort of nugget of this amplitude is this moduli space integral. Okay. So this x is the so-called modulus. So the way you represent this is an open string diagram with a disk with 4 insertions. Okay. So these are the 4 gluon insertions. There will be some specific vertex operator for them, and yeah. So the one modulus is that you can fix, for example, 3 of the points. So in the upper half plane representation, you can fix one of the points at 0, one at 1, another one at infinity, and this last one, which is the modulus, is located at x, and x goes between 0 and 1. Okay, so we have, even though you have 4 open string punctures, you might have thought there are 4 coordinates to integrate over, but 3 of them can be fixed using this Mobius transformations SL2R to 0, 1, and infinity, and this 4th puncture is the one which is moving. Okay, so that's x. Okay, and you integrate over x, so the moduli space here is the line segment 0 to 1. X equal to 0.
So why this 0 is special?
Yeah, so that is just happens to be, in one of these color orderings. If you look at the different color orderings, the 1 will also be divergent in some of them, because there are 3 different color orderings here, and in 2 of them this one will be divergent and the other one will also be. So the moral of this basic computation, which is there in the first formula that started string theory, Veneziano, this is basically the Veneziano amplitude, is that boundaries of moduli space give divergences. Okay, so it's not true that you write a moduli space integral and you can go home. Okay, you need to do something. Yeah.
The usual way people would say that you just analytically continue.
Exactly. So right. Yeah. So that is satisfying in this case. So here you have some space filling D branes, and you have some S. S is the Mandelstam S, and it's the square of these momentum vectors. Now you can think of, so P1 is a 10-dimensional momentum, right? And you typically think of them as real, but you can think of each component of P1 vector as a complex number. And by going to suitably complex values of components of P1, P2, P3, P4, you can stay on shell, but make S and U both negative. Okay? So you say that you define the integral for those complex unphysical values of momenta, and then the real answer is just the analytic continuation of that. And that is why people write down just the beta function here. So this will be something like gamma minus S, gamma minus U divided by that. But the point is you have momenta available to you. Okay, in this case, you can do that. And that's how people have done it. Here some exact formula is known, so
Sorry,
yes.
Staying on shell is important because it continues to keep the operator
1, 1, exactly, right. So you can complexify the momenta, stay on shell, still have S negative and U negative, and okay, that's it. So for this problem, it's not, but the point is, if you're doing this at one loop, let's say, you will not have some simple gamma gamma divided by gamma expression. This analytic continuation is not going to help you if the integrand was way more complicated. Right? In this case, we just happened to be lucky that Euler was there 400 years ago, and he told us what the answer to this integral is. Right? Yes.
These are IR divergent.
Yeah. So I'll come to that. I have not mentioned that yet, but okay. So this is the problem. Okay. So the boundaries of moduli space are always going to be problematic, and they give rise to divergences. There are actually many ways to see this. One is that when x goes to 0, these 2 points are coming close to each other. Okay. So from the world sheet CFT point of view, boundaries are where the OPE expansion is true. Okay, are governed by the OPE expansion. And you know that typically the leading few terms in the OPE expansion are negative powers of the separation in the 2 points. And that's another way to see why these would be divergent. It's coming precisely because of that you have these 2 operators that are coming close to each other, you fuse them, you do the OPE, and in the OPE, in the coordinate x, there are negative powers of x in that thing. The singular terms in the OPE exactly lead to, so there are singular terms in the OPE, and now you're trying to integrate over this cross ratio variable x. So that is why this power is negative here basically. Okay. So that's the worldsheet point of view. So it seems like it's some kind of UV divergence on the worldsheet CFT. But from the space-time point of view, these are IR divergences, because you can show that. So let me write the formula here. This integral 0 to 1 dx x to the minus s minus 1 minus x to the minus u minus 1 is gamma of minus s gamma of minus u divided by gamma of minus s minus u. So there are poles at s equal to 0, 1, 2, 3, etc. Right? Because of this gamma of minus s due to this factor. Okay. So poles represent physical propagation of on-shell particles, and this is nothing but the tower of open string states, right? And so what you are seeing are that this divergence, you would not have a pole if this integral was convergent, or yeah. So the fact that at physical values of s, when s is positive, let's say you collided these particles such that s was exactly equal to 2, right? Then the answer is really infinite. So that is another way to see that these divergences kind of have to be there in some sense. You see, if you want to have poles in the scattering amplitude at physical values of the scattering parameters, you have to have some divergences. Okay. Sorry? For some physical kinematics, yeah, exactly. Not all, but some, yeah. Right. So these are why these are sort of infrared effects in space-time. Because a pole in a propagator really represents the fact that an on-shell particle got produced, propagated for a long amount of time, and so the amplitude for that process was very big. Okay. So kind of UV divergences on the worldsheet lead to these IR effects in space-time. And we know that IR effects are not artifacts of using a Lagrangian or something. Like IR effects are really there in the physical theory. Like they're telling you, something physical, that there was an on-shell particle, or if there are IR divergences, then you have to maybe reconsider what you're calculating, calculate some inclusive cross-section, etc., etc. Okay.
From this Raghu, is it clear why I would expect this pole to get integer values of the 1 plus beta square?
I think you can see it from this formula, because
From the integral it's obvious.
yeah,
Like to argue whatever it is in the pole in the propagator and all.
yeah.
There is it clear why I expect them to be T1 plus beta square equal to integer?
I don't know of a direct way. The only way I would know is that I know the tree level spectrum of strings, right? So that's a separate calculation from, that's a separate calculation.
Here I cannot tell.
From here I cannot tell. If I look at this integral, you can tell. Yeah.
Otherwise I don't have an expectation of anything.
No, not just from,
It comes out this way.
right. But if you believe that you calculated the single particle spectrum correctly, then yeah, of course. Because otherwise, if you just say I'm colliding, 4 gluons, the Veneziano amplitude is not the unique amplitude. You could just have a gauge theory amplitude for 4 gluons, right? Yeah.
When you say that you can see that from the integral expression,
Yeah.
can you say how?
So for this one is maybe a bit more complicated, but maybe let's try to simplify the problem and try to see 0 to 1 dx and just x to the alpha. Okay, so this integral. So this is convergent when alpha is positive, right? So the answer is 1 over alpha plus 1, right? So you see that this thing, when alpha equals minus 1, this has a log divergence, but in this analytically continued form, it shows up as a pole at alpha equal to. This is like kind of how dimreg works. Like in dimreg, you analytically continue something on the left-hand side, and what was supposed to be divergent shows up as poles in the epsilon. So this kind of like that, exactly like that. Yeah.
Along those lines, if you try to regulate the divergence in a dumb way,
Yeah.
by putting a cutoff,
Yeah.
generally power law divergences can be removed.
Can be
but
go.
logs
Yeah.
cannot. And
Right.
if you take that for any integer s,
Mhm.
you get log divergences,
Okay. Yeah.
because the 1 over epsilon square.
Yeah. Those will be killed, but ultimately there will be some log. Yeah. Exactly. Yeah, so those poles are there. So
Conformal invariance also hates a lot.
yeah. Okay. So yes.
So I'm just trying to understand that boundary of the modular space that x is going to 0, that is
Yes.
a particular pole in S, let's say a particular finite.
Not a particular pole, but a bunch of poles. Like all of the things are sort of due to that. Yeah.
I'm just trying to think that it will be some Feynman diagram, like one particular Feynman.
Yeah, yeah. Yeah. Go on. Finish your question. Yeah.
So there I'm not able to see where the divergence will be there in that sense. Is the divergence just the pole in the S then, just the way that you wrote down the final equation, or?
I mean, here what I'm saying is that the OP expansion is an expansion in X, right? So you will have some operator A of X, A of 0, right? And for example, the first term will be 1 over X to the 2 delta of A plus dot dot dot, right? The delta of A is a positive number. So this is some divergent thing. So here I'm just trying to explain. I'm not trying to sort of connect everything because this is not my main example. But the fact that this is a negative power of X and the power here will depend on S, because typically what enters in these A's are these exponential operators, e to the I k dot x. And the dimension of these operators is related to the square of these momentum variables. So what you get is 1 over x to the sum s, which is basically this thing, right? So the s is coming because s is related to these momenta, and in the vertex operator you have e to the I k x, and the dimension of that operators is governed by this k. Okay. Yeah.
So this boundary of moduli space in divergences is true even when the moduli are
Not positions, yeah. Yeah, so here it was positions, but you can imagine that, for example, in the annulus, it's very easy to imagine that you have an open string, and if it propagates for a very long time, so that will be a cylinder which is very kind of big this way. Then if you have massless states just propagating in a loop, that will also give divergences. So even if the moduli are associated to some, Riemann surface and not just positions, there will also be divergences. Like a very thin annulus or a very thick annulus, things like that. Yeah.
So, but Sandeep, you have a way to see that I can see that the long divergence will come to ICTS 0, right? Because it will be kind of thing. But if you have some other integer, how do I see this?
Okay, you start this. Okay, I don't know. Okay.
Can I suggest we delay this because it's not going to be the main point, and we can discuss it later. Yeah.
No, I mean, it would be nice to see that there is a sequence of poles, integers particularly.
Yeah. So I agree that's an exercise maybe I should have done, but I'm not prepared to do it, on the board. So maybe let's.
Once we do later,
Yeah.
see maybe it holds up.
I think it will be important to have the second factor, because if you just have the one factor, this integral is exact. So you'll just get a single pole here at alpha equal to -1. So to get the sequence of poles, it will be important to sort of do something with this factor. But I did not prepare that part. Okay, now one point is that, if you have a DP brane, so why D-instantons are special? So you raise the point that you can analytically continue in momentum and so on. But you see, if you have a DP brane, let's say this is a DP brane, the open string fields propagate on the D brane world volume. So these momenta, or these p's, are valued in R1, P. Okay, because it's a p plus one dimensional field theory and it's R1, P, right? So you have some momentum. But a D-instanton is the case when p equals -1. So in some sense, its world volume has dimensionality 1 plus p, which is equal to 0. So the whole D-instanton world volume is just a point. So the open string states that are attached to the D-instanton don't have momentum. There is just no vector available for the momentum. So you'll see that you'll be stuck, like you just don't have a momentum in which you can analytically continue. Okay, so that's one kind of preview into why D-instantons are special. And okay, that's just a vague comment for now, but it kind of plays out in a technical way as well.
Can one do a analytic continuation dimension?
In P, you mean? Maybe. It's an interesting idea, but I have not thought about it. Yeah. It may be possible to do in P. Okay, yeah, I don't know. All right, so that's about tree level amplitudes, and tree level amplitudes have divergences, and thanks for all the questions, like please keep them coming, okay. So now let's discuss one loop. Okay, so if you're doing the same thing, but at one loop, okay, things are more complicated. Okay, so let's take the same amplitude and try to do next order. So one loop of the same amplitude. In the same theory, in the type 1 theory and so on. And so you can show that there are certain number of moduli in this diagram. In fact, there are 4 moduli. So it's a 4-dimensional moduli space. Okay, so it's way more complicated than just an X integral. Okay. And in fact, the integrand on the moduli space was known 50 years ago or whatever. Like, it's simple to write down because these are just some free fields on the world sheet, and the annulus amplitudes on the free fields are well known. So the integrand is well known. And it's real. Okay. And when I say it's real, I mean it's real on these physical, for physical scattering, things. Okay. Sorry.
So you have to say moduli could be complex, right? When you say 4, that's a real moduli.
Yeah. So I'm parameterizing the moduli space using real coordinates. It's a 4-dimensional real manifold. So I'm parameterizing it using 4 real coordinates.
And everywhere in that moduli space, this is real.
Sorry.
Everywhere in this 4-dimensional.
Yes. Exactly. Yeah. Now,
one of them would be like the twist, right? Or not?
So in the annulus, you don't have the twist. You have that on the torus. So we are doing one loop of open string. So this is an annulus amplitude. Annulus does not have the twist. Yeah.
Which boundary is the annulus based on the operator?
For this rough argument doesn't matter. So you have planar and non-planar kind of amplitudes. Let's say you insert all 4 of them on one boundary. Okay, that's fine. Sorry?
So it's not a discrete modulus. It's just something you put in the on the left side.
Yeah, I mean the idea is that there's this SO32. If you imagine this was SON, the way you distribute the particles on the 2 sides of the annulus is just a planar versus non-planar amplitude of the same.
They come with different powers of
N, if this was N.
exactly.
Yeah. Okay. Now you see this is already a problem because, and this is what Sebastian and Lawrence have emphasized, that if this integral was convergent, you would get a real answer. But you know that one loop amplitudes have to have imaginary parts because of unitarity. Okay, because one loop amplitudes can be cut, so they have to have imaginary parts. So a fully real answer would just be inconsistent with physical principles. Okay, so in this case, there's a different analytic continuation which is available, which is maybe related to this momentum continuation, but there is this so-called Witten I epsilon. Okay, in that, what you do is you think of the sum of the moduli as proper times of the string propagation. You see, because how much time the string propagates for, that is part of one of these moduli, right? Just like the length of the annulus. And the idea is to complexify that time. So complexify that Schwinger parameter. So identify which combination of moduli corresponds to world sheet time, and complexify that. So this kind of regulates it. So basically it means that you normally we think of the moduli space in this case as 4 real dimensional, but think of that as complexifying everything. So you complexify it into a 4-dimensional complex space, and then your integration cycle is some middle dimensional thing in that 8-dimensional space now, and you can choose that appropriately to give a convergent answer. Okay, so that's the idea. So what it means to complexify the moduli is just that the Riemann surface you have doesn't have a real metric anymore, but in general can have a complex metric or a Lorentzian metric. And in those things, like, it's possible to get finite answers. And it's only recently that Misera and Eberhardt implemented this procedure for this amplitude and produced plots, numerical plots of the amplitude as a function of scattering angle and the Mandelstam energy, for example. So until like 2 years ago, these plots were not there, because even though you know the integrand, doing this 4D integral was just impossible. Yeah, so they've kind of first understood this I epsilon prescription, designed a new contour on which the integrand would be very fastly convergent, and then did the numerics. So the trick to get convergent numerics is the analytical insight of how you deform the contour in the first place.
Can this be done by analytically continuing the momenta?
Maybe, but the question here now becomes practical. Like, is there a practical way to do that computation and produce plots? So now they have set the bar high. Like, they have actual pictures, which is agreeing with the Regge asymptotics and everything that you expect from the amplitudes. It's giving the right image. So for example, people had calculated the imaginary part of the one loop amplitude is easy to get using unitarity cut methods. And the numerics they are doing are consistent with those old, sometimes analytical results. So there's all of that, but what I'm trying to emphasize is that the computation of even this one loop amplitude, doing this 4D integral is non-trivial and was only done recently. And yeah.
To understand, would it depend on which 4-dimensional surface in 8 dimensions you choose? Besides the contour, is there?
No, I think there is. So you see, because the original integral is ill-defined, you need to make some choice, some physically motivated choice to begin with. But as long as you deform that contour, just by Cauchy's theorem, the answer will not change.
So maybe local changes don't change.
Yeah, but some crazy change, if you do incorrectly, then of course the answer will change. Because of course the original contour is not correct. That is, it's ill-defined. So you first need to modify it using some physical prescription like this I epsilon, insight, how you deform it. But then after you have got the right contour in one representation, you can do homology deformations of that, and that's okay.
Sorry, what is this combination of, I don't understand this, which combination of moduli corresponds to one sheet?
Yeah, so that depends on how you coordinatize the moduli space. See, because moduli space is some 4-dimensional manifold, so the choice of coordinates on that is not unique. Okay, so you can pick whatever coordinates, somebody else might pick other coordinates, somebody else might pick other coordinates. So, and this was one of the points of the lectures, to show you in a very concrete example how you identify this combination.
No, my question was why does it correspond to time? What is time?
So just imagine, in this annulus, so you have an open string of length pi, right? Just imagine the empty annulus. It propagates for some time. It's usually called 2 pi t, right? And then you make an identification. So this way it's identified. So this is the cylinder amplitude. So it's an open string propagating for some time and then identified. So this t is the modular parameter of this annulus or the cylinder that you're getting. But here it corresponds literally to the open string time. So this is what I mean. And in more complicated examples, it will be more complicated. But something like this will be true, that there will be some long strip of open string and then maybe attached to something else on the sides.
One more thing.
Yeah.
So the integral is over a line or a 4-dimensional plane?
It's a 4-dimensional space with some weird singularities at various places.
It's not like this integral.
Well, so this is a 1D integral, right? So it has boundaries. So there's a 4D space. And I mean, even this is from 0 to 1 is some artifact, right? I can do a change of coordinates in which this looks like minus infinity to infinity, like some tan of x or something, or tan inverse x. So
when you see make the space-time,
the string world sheet, yeah.
Complex,
Yeah.
that will also mean that the project dual momenta will also be analytically quantified as the origin said.
Yeah. So you can do all those things, yeah.
So my question is, so this is going to be basically a kind of a phenomenon type of integral.
Yeah.
With the propagation
Yeah.
some quantity stuff downstairs.
Yeah.
So in momentum. So I think so. Since you talked about homology cycles and also, so I want to. So should I think of them as a homology cycle of the algebraic space, algebraic variety that's given by those denominators?
No.
Cycles are these? Because it's
No. These are homology cycles. For example, here t is a real parameter, right? I'm very concretely, t is real here, so it's one dimensional. But imagine that you complexify t, right? So if I wanted a Lorentzian time evolution, this t would have to be imaginary or something, right? So that's what I mean by complexifying the moduli. It's complexifying this x. So here, x is real. It just goes from 0 to 1. But what Witten is complexifying is this x itself or that t itself. Right. And then it's the homology of that space, of the middle dimensional cycle in that complexified space.
Which complex? So as it is for Cn, there's nothing like so everything is trivial, right? If I was just doing
Yeah. So here,
something else one is doing so that I get non-trivial homology.
Yeah. So these moduli spaces are not C4 or Cn, right? They have some interesting singularities.
So that must be coming from the propagators.
Okay.
That's what I was saying. Where are they coming?
I guess they are coming. The choice of the cycle is dictated by, just writing the. Maybe what you're saying is you write the propagator as a Schwinger parameter integral, and that Schwinger parameter integral gives you insight onto where that cycle should go. So it's about the Schwinger parameter representation of the propagator, and the point is that those Schwinger parameter are like this t, right? So that's basically. In QFT, right. Okay, so that's also not what we are going to talk about because it's also, well, I'm just saying that there are all these problems and there are, things people have done to address these problems in string amplitudes, and which is sort of tying into current research as well. Okay, so another example. So I want to spend some time on this to just emphasize what all kind of problems exist in string perturbation theory. Yes.
Imaginary part argument.
Yeah.
Strictly speaking, the imaginary part, you have a cut, right? You have a branch cut.
Yeah.
From the real line.
Yes.
So
Yes.
in order to prove that imaginary part, you want to take I epsilon for momentum.
Right.
So that will tell you, right, how, instead of, finding this cycle with some principles, you can have just one uniform principle that you just take your momenta, which are the external variables,
Yeah.
just move them. So
I agree.
This is S plus epsilon.
I agree. So that in principle will also give you the right answer. But what I'm saying is that has not been practically implemented on a computer. So if one could do that, that would be a cross check of their results, for example. That's correct.
The idea is, so you do the same analytic continuation in the
Momenta.
that you should do for computing Feynman now.
Exactly. Like S plus I epsilon. Just like Abhijit is saying, right? Because on the real S, there is a cut. So you know that there is some ambiguity. But so if you complexify the momenta and you are able to do the calculation in as much detail as they have done, then I think one would find agreement. I agree. Yeah, the hard part of that calculation would again be because you would need to take the Mandelstam variable real but all small imaginary part, right? And then you will see some crazy numerical behavior because on the real axis it's diverging. So that is why this clever contour choice and deformation can.
What I'm saying is that there is no choice. I mean, you can get around, if you want to do some complicated calculation,
Yeah.
some high-dimensional space,
Yeah.
you complexify the whole thing, find half-dimensional cycle, how, right? So instead
Yeah,
of
yeah.
that, you have this general description, and once you find the topological class, you can just find the saddle point,
Yeah,
and deform it, and so on.
Yeah,
But
yeah.
at least
I agree.
unambiguously fixed like that.
I agree.
Another question you asked.
I agree. So I completely agree, and that's actually a kind of a critique of the paper of Eberhardt and Misera, that what they did was very heavily tied to just the one loop amplitude. So their contour prescription will not, there's no natural generalization of it to genus 2 or genus 3 or higher loops. So they specifically wanted to work with the one loop amplitude and practically just compute it. And there, they use some tricks and things that are very specifically tailored to that one loop computation, and were able to get that answer. Yeah. So you're right, and I agree. okay, so here is another issue that comes. So usually we say external states must always be on shell in string theory, okay? But you have to realize that this is a chicken and egg question, because the mass of a heavy string state gets corrected in perturbation theory. The tree level mass that you compute is shifted by corrections of order G string. So saying that you put the external state on shell is, which mass do you use? Do you use the tree level mass? Do you use the one loop mass? Which mass, like, okay? And okay, so that's a question. So imagine like some string which is coming in, okay? It's an open string. And what can happen is that you need to know what momenta to put it, okay? So typically what you will do in Feynman graphs is you say, I don't care about the perturbative corrections to the mass, they will get generated from the Feynman diagram. Right? That is what you would say in QFT. Yes. Which one?
Left board is not visible on the right board.
The whole thing is not visible?
Yeah. But the right board can be moved around.
You can take it up.
Okay.
There's a bar that you can press.
Oh, but I see there's quite a limitation on our filming.
Yeah, here, this small
It's
camera.
because of just this.
Right now that's what it is. If you press the
Okay. Yeah, yeah. Sorry?
Check, yeah, if not, then leave it.
Someone told me that.
Okay, that's fine. We'll stick to this. Okay, so you know, you typically have some open string coming in, right? And the mass corrections and all are perturbative effects, so they'll be at one loop. So you might have some diagram like this, where the open string splits into two, right? And then it continues its journey, and then you know, it merges with another one, and then you have this process here, right? So this is the four strings interacting, but this guy is undergoing some kind of loop correction. Now in Feynman diagrams, of course, this would just be drawn by this thing, right? Now, even in QFT, you say, you know, you amputate the external leg, fine. So this one is on shell in an S matrix element. So this guy satisfies p square plus m square equal to 0. So you don't put its propagator. But this guy is an internal leg. So you have to put its propagator. But by momentum conservation, this leg is carrying the same momentum as this one, right? So this one has a propagator which is 1 over p square plus m square, which is 1 by 0. Okay? So this diagram is ill-defined, even in QFT. Okay? And the way to deal with it, we all know what you do. The point is you have to then add up more corrections like this, right? Because here, this one is on shell. You don't write this propagator. But by momentum conservation, this line is on shell. And by momentum conservation, this line is also on shell. So here, this propagator is 1 over 0. And this propagator is also 1 over 0. And so on, right? So this is the logic behind the 1pi resummation of this thing. So you write all of these graphs, and you do the 1pi resummation. And then you are supposed to get the mass shift, the real mass shift, and the decay width, and everything, right? But the basic problem is coming from the fact that you could not have calculated this just at a fixed loop order, because this is just 1 over 0. Okay, so you need to do this resummation and have that 1pi whatever that we learn in QFT at the back of your mind. And the divergences will be more and more worse. Okay, so it's not usually said this way, but this is the reason that you have to do this. Yes. But how do you compute them in perturbation theory? That's fine as a non-perturbative or something statement. But the bubbles are the ones that give you the mass shift and the renormalization of all those things, right? So in practice, you have these things. Then you renormalize the mass and Z in such a way that you don't include them anymore. But at first go, they are there, right? Now, the point that I want to make is that these are only specific Feynman diagrams at this loop order, right? So at this loop order, there are other vertex corrections and so on also. But in dealing with this problem of mass renormalization, only a specific Feynman diagram is important. Okay, like this vertex correction, for example, here or here will not be important. So there are specific Feynman diagrams at each loop order that you need to isolate and resum to get this mass correction. Now, in string theory, the problem is all G loop Feynman diagrams or all G loop contributions, sorry, maybe the entire G loop contribution comes from a single integral, comes from one big moduli space integral. Okay, so that same moduli space integral in the QFT language will have both propagator corrections, vertex corrections, external leg corrections. Everything is kind of mixed up in a soup in this big integral. Okay, so if you want to solve this problem of mass renormalization, you will first have to look at the one loop moduli space, isolate in which corner is it looking like this, then go to the two loop moduli space, isolate where it's looking like this, take all those different corners at different genus, add them up, right? That is what you'll have to do. So that is a problem in the way we write amplitudes in string theory, is that all the genus G corrections are clubbed into one thing. And they are divergent from different corners, and those divergences physically mean different things. Okay? So it's because of this mixing between loop orders that you need to deal with IR divergences. You need to carefully chunk up your moduli space so that you can identify, look, in this corner of the moduli space, my Riemann surface is looking like this. So I will interpret that as this Feynman diagram. Okay, and so on and so forth. So that is why the Feynman diagrams are still important even in string theory.
So is it right to say that if we're calculating amplitude in a QFT, then we can just stick to a certain Feynman diagram?
Yes.
So that
Yes.
no external bubbles and so on.
Yeah.
But in string theory moduli space integral, there naturally be things like that. And
Yes.
there's no way to just stop
Yeah, exactly. Yeah. Yes. Yes. There are naturally diagrams that look like the ribbon. There are naturally open string world sheets that look like this.
So there's no LSC-like thing that you can do for a string amplitude. Is that?
I mean, I think I'm not appreciating your perspective. I mean, LSZ is some theorem, but to actually practically implement it, you do calculate these diagrams, right? I mean, you calculate this leg separately, right? But honestly speaking, it's a part of this diagram, right? It's even there in QFT.
What I'm imagining is that the external leg with bubbles goes into the information of what exactly was scattering. What is the definition of that one?
Yeah, I agree. But that information, how do you capture it in perturbation theory? Is by doing these same Feynman graphs, right? So at that level, it's the same. There is no difference.
Actually, even internal legs
Yeah.
will have mass renormalization.
Yeah.
And then
Yeah.
you have that issue there also.
There the issue is a bit milder. You see, because if I take a diagram and I put an external and I put this bubble here, this one is not necessarily on shell. So its propagator is finite. So it doesn't have this 1 over 0. Right? It's some 1 over something finite because it's typically it's off shell.
But you have to sum these, but it's okay.
But it's okay. Like it's not as severe as the external leg problems. Yeah.
Tangential question. Is it possible to compute string theory amplitudes from some sort of quantum effective action or worksheet where you do the sphere integrals,
Mm-hmm.
I mean you absorb everything
Yes.
to the CFT and the renormalization of the vertex operators somehow?
Yes. It is possible. So the 1pi effective action, you can construct it. But again, the practical way to construct it would be to do the 1pi summation of the graph, and club them into some vertex, that effective vertex that you will use.
Right. No, but after doing all that, can everything now be written as some sort of an effective CFT?
Oh, effective CFT.
Worksheet CFT, so that now I just do a sphere integrals. I just do sphere integrals and
But you mean a local CFT in particular?
yeah, maybe.
I have a suspicion that if you write it as a CFT, it will be some non-local thing. Like if you want to just get everything from a sphere amplitude and you want to club.
As long as I have ability to compute correlation functions of that, right?
Yeah.
Some correlation functions, and then vertex operators are also corrected somehow.
Yeah.
That kind of.
I think formally you are right, but I don't know of a very efficient practical way of packaging that information to use it, to leverage it.
Using the all genus 1PI.
Yeah, exactly.
Effectively is here.
Yeah. I think that exists. So formally that exists. And
as a string field theory, you can do it, right? But I was wondering whether you can write it
as a world sheet CFT. So what I'm saying is I don't think it would be any kind of a nice CFT. At least that's my naive expectation.
Because that's one way of absorbing all these.
I agree. I agree. But I don't think from a world sheet point of view that operation will be very nice. Okay. So this I'm trying to emphasize that there are certain very physical effects in QFT that mix different orders of perturbation theory. And so it's very important to know what those divergences physically mean, and then you have to need to chunk up the moduli space appropriately to deal with these things. Okay.
Also,
Yes.
From a practical point of view, you want to know what the physical masses are.
Exactly, right. So see, and you will be stuck because in this external string diagram, you will just put in, what will you put? You don't know the first correction, right? So you only know the tree level mass. So you'll start by doing that calculation, but then you will see divergence here, right? There is no way out except to follow that LSZ logic, right? And the same thing happens for these tadpoles, like or vacuum shifts or something. So I won't go into that, but similar thing will be there for those quantities.
Can I confirm something? So are you saying that one way these diagrams where the bubble is sitting outside the connected part and is sitting inside the connected part, there's no way to distinguish that from the moduli space?
No, what I'm saying is that the moduli space contains all those Feynman diagrams, but the ones in which the bubble is on the external leg are kind of more severe problems.
Yeah, so from the QFT logic, you want to put them into some vertex factors or something, think of them as renormalized external legs.
Yes, as a renormalized mass. Yeah.
So can't you do this moduli space integration region by region, like?
Yeah, that's what you have to do, but that's what I'm saying, that it is important to split up the moduli space into regions. You cannot just think of the moduli space as one big object and one big integral. So the chunking up of the moduli space into these different regions is important. But that's the point of this comment. Because typically you don't see it that way. You see it that the two loop amplitude is just some integral over some 12-dimensional space or something like that, right? Okay.
Thanks.
All right. So another, maybe I'll move this more down. Yeah. Sorry? No, not this problem. These are just all motivations. Like I will do only D-instantons in more detail, but these are just sort of invitations, to what are the kind of problems that exist.
Does it have a solution?
Huh?
Does it have a solution?
Yeah. So Roji and Ashok have papers from about 10 years ago now, in which they did this. So this problem has been done in the some heterotic string compactification, etc. Yeah, that and also the vacuum shift one. Okay. So the next problem is the scattering of D0 branes and strings. Yes. Yeah.
Fundamentally, sometimes it is quite useful to think of effective action, right?
Yes.
Low energy effective action.
Sorry?
Low energy effective
Yes.
where you expand out these scattering amplitudes in derivative expansion.
Yeah.
Is there a way to somehow carry that out in string theory? Instead of, for example, in that moduli space integral that you wrote down one loop, not one loop, even tree level. There I got the full answer as a closed function of SNT, right?
Yeah.
I could expand this at low energy.
Yes.
Right? And then I was wondering if you did that for the integral. Is it that the modular space integrals, do they take easier forms so that I want to compute them term by term, and some of these questions can they be relieved a little bit?
Yeah, good question. The only thing is, even if you take the physical low energy limit in which S will still be positive but small, that integral is still divergent, right? So these two seem to be two different problems. The fact that the low energy limit from the point of view of this integral will not help you because S will still stay positive, right? So
Isn't that one way to say that if you have poles in the low energy effective theory, then you would expect divergences to remain
even in the low energy, yeah. Right.
Otherwise, you could get rid of that.
Okay. So the next thing where you need this is scattering of D0 branes and strings. Okay. So typically how you model a D0 brane is just some heavy particle, okay, that just sits there forever. So this is time, and this particle has a mass in perturbation theory which is very heavy. So its mass is 1 over gs. Sorry?
No,
So you,
it's a deep set something of the pole, but with low energy expansion, I wouldn't have any problem, just see the polynomial terms in SAT. The pole
well, except the S equal to 0 pole, except the S equal to, except the,
Yeah, the other ones you get rid of. Okay. That's minor poles. That's true.
sorry, so there's m equals to 1 over gs, and then you might have some closed string which sort of comes in, hits it and goes back, right? Now this closed string has a mass which is of order 1. By that it means gs to the power 0. So it's a very light thing that hits a heavy thing, and at tree level it just bounces back, okay, with its momentum. If it was plus p, it just goes as minus p. So that means momentum is not being conserved in this process, okay. And at tree level that's fine because the boundary state formalism allows you to calculate these things. But really at this thing should get a kick. It will be a small kick, but after this collision happens, the D brane has to change its velocity, okay. And just the normal formalism in which how we write D branes as a boundary state just does not allow for that change to happen, okay. So again, to deal with this, you have to write down some kind of field theory on this D0 brane world volume, which involves a cubic coupling between the position of this D brane, that's 1 degree of freedom, and this closed string field. And the way you calculate that coefficient is again using string field theory. And this was again a recent paper of Ashok and Bogdan in which they have done this just this year.
Just say
Yeah.
how do you do it?
So basically what they do is, so from the worldsheet point of view, this appears because when you try to calculate, so let's say you even do a simpler calculation what they did, just a 3-point amplitude. So you have a D0 brane, a closed string comes in, just gets absorbed. Okay, so so at the disk level, this would just be a disk 1-point function of this vertex operator V, right? But at the next level, there's an annulus 1-point function in perturbation theory, right? So this thing has infrared divergences that are precisely telling you that you are computing something wrong, right? So then you have to allow for the final state of this D brane to change, and that cures this infrared divergence. And the way they did it was to write an effective quantum mechanics on this world line, in which the degrees of freedom on the world line are just the transverse positions of this D0 brane. And there's a cubic coupling between the closed string field and that degree of freedom. And you're just calculating some coefficient in that effective action, which would be the 3-point amplitude, correct 3-point amplitude. Okay. But the point is, again, the infrared divergence comes from this diagram, which is a higher loop diagram. And the infrared divergence is telling you that your scattering states that you put are not the correct ones.
And they computed that world line, whatever quantum mechanics from string.
So you use string field theory as applied to this diagram to work out some coefficient in this effective theory. Okay, so you see that the worldsheet formalism is just ill-equipped to deal with this problem.
I have a question.
Yes.
Is the same as saying from the worldsheet you can't describe in the large gauge transformations in the target?
Sorry, which gauge transformation do you mean?
through the space-time, you have these large gauge transformations which move the asymptotics or whatever, right? So that you can't describe from the worldsheet. Is that one way of saying this?
Sorry, gauge. You mean some diffeomorphism gauge or SO32?
Large diffeomorphism state, let's say, yeah.
I mean, this is not to do with diffeomorphism. This has to do with the fact that the D0 brane has a mass which is kind of non-perturbative in GS. So you cannot change that, right? In the string theory formalism, the way you describe a D0 brane is as some Ishibashi state. Like there is some boundary state. And in that boundary state, you put in the position of the D0 brane. Okay? And the transverse positions are fixed. And in this direction, it has an arbitrary, the momentum is 0. And in this case, it has arbitrary momentum. So there's some fixed boundary state that just the worldsheet formalism does not allow you to change. That's the point. I don't think it's directly related to diffeomorphism or large gauge transformation or anything.
The change in velocity will be order GS.
Order GS, exactly. So it's small. Right? That's why it's the next diagram that is relevant here. Yeah. Okay.
So I can't think of the infrared divergences as related to the QFT infrared divergences.
Well, but not all infrared divergences are large gauge transformations, right? Your previous question had to do with gauge transformation. Infrared divergence is not the same as.
Related by soft events or whatever, right? So that's what I meant.
But those are two different things.
Okay.
This is an infrared divergence in space-time, but it's not related to large gauge transformation. Or at least I don't know how it's related or if it's related.
Okay, thank you.
Okay, so the moral of the story here is that SFT is nothing to be scared about. Is just
That moral doesn't follow.
the right way to do string perturbation theory.
Maybe the right way, but you need bigger boost.
It's just that the worldsheet formalism omits certain things, and this just puts those pieces back in. Okay, that's it.
There is other aspect that is usually associated in field theory, which is background independence and all that.
Yeah.
So those aspects are not just, we are just talking about this.
Yeah, I'm just focusing on this perturbative aspect, yeah. But even those background independence proofs and so on are still perturbative. Like you start with a background and you go to a nearby classical solution. And you can try to integrate that, then say that, okay, I have proved it. But everybody just works in perturbation theory. The only non-perturbative kind of result that is known in string theory is if you are just doing open strings at classical level. So there's a closed form action for classical open strings, which was written down by Witten. And this guy, Martin Schnabel, found an analytic solution to the equations of motion of that theory. So it's an analytic solution which is very far from just setting all the fields to 0. And so that's one example where something non-perturbative is known. But that involves only open strings as a closed system because you're working at the classical level, at the tree level.
Basically the decay of the brain, right?
Sorry? Yeah, the decay of the brain. Yeah. So that solution is known.
The background where the brain is present. So in terms
Yeah.
of the
Right. So you start with so there's a string field psi. When it's equal to 0, the interpretation of psi equal to 0 is that there's a D0 brane, let's say in a bosonic string there. And then this new solution, which is psi equal to some very highly non-trivial function, is the space-time configuration where the D0 brane has decayed. Okay. So that's the only thing where the non-perturbative thing is known. Otherwise, everything is just perturbative. Yeah.
Historical thing. You know, in the old days, for vacuum shifts and all, there was this thing called Fischler-Susskind.
Yeah.
I don't know. It was very confusing and so on, but
Yeah. So this makes it very precise. Exactly. You see, even there, they were talking about the fact that different graphs in string theory can be divergent, but then when you add everything up, it was kind of supposed to be finite, right? And in this D-Instantons, there was a very, very precise implementation of that in the paper of Balthazar, Rodriguez, and Yin. So they started this story of studying instanton effects in this 2D string theory, and there were a few different diagrams that they had to add up for some scattering process. and they saw that one of them has a log divergence, the other one has a log divergence, but they come with a relative minus sign, so they are supposed to cancel. But now because they are treating this diagram and this diagram completely independently, by diagram I mean for them it was different moduli spaces. So let me just draw here. One moduli space was the disk with two punctures. So in the traditional worldsheet formalism this will have some integral, and another one was annulus with a single puncture. Now these two have the same order in GS. So this one is 1 over GS times GS square. This comes from the boundary and this is the two punctures. Here it's also order GS just from this. So you have to add these. So you have one less puncture and one more boundary. So you have to add these two. This has a log divergence, this has a log divergence. But unless you have some more structure on this, it will be impossible to fix a relative constant that you could miss, in cancelling that. Because it's log of x over something always. So you'll put a cutoff here, you'll put a cutoff here. How are those two cutoffs related? And the string field theory version of constructing these more complicated Riemann surfaces recursively gives you that hard relationship between the cutoff here and the cutoff here. So this is Fischler-Susskind, that the log is cancelling, but then you make it much more precise by saying that this is how the cutoffs are related, and here is some finite log 4 that they were missing, right? So that was Ashok's first paper after BRY. They had some unknown constant that they couldn't fix, but they had some matrix model, and the matrix model gave them some number. But then Ashok said, no, it's not that number, it's correct, but it's minus log 4 or something. It was 0.32, whatever. Anyway, so this is Fischler-Susskind, it's precisely that. And here, this actually brings out another point that at a given order in GS, you can have different topologies also contributing, because in this. Okay, all right. So, so now this motivation part has ended, and hope I have convinced you that at least there is some merit in learning this subject. Okay, so now we will go to the actual hands-on parts of the thing. Okay, so let's go back to the Veneziano amplitude. The Veneziano amplitude had a moduli space in X which was between 0 and 1, right? So this was the and this is X, so this is a moduli space. Now we saw that there are some divergences coming from this region. And typically in the most general calculation, for example, if you add up the different color orderings, there will also be divergences from here. Okay. So you divide up the moduli space, your 0, 1, as a union of 3 intervals. So let's say 0 to epsilon. I mean, this doesn't matter, the fact that, and then epsilon to 1 minus epsilon, union 1 minus epsilon to 1. Okay. And I was doing this in this color ordering where there was 1, 2, 3, and 4. And what you do is that in this region, so you split up your integral into 3 different regions. You have an integral from 0 to 1. You literally write that as 0 to epsilon plus epsilon to 1 minus epsilon, and then 1 minus epsilon to 1. Okay. So the full answer is this. These parts are a little bit divergent. Now what you do is you realize that this thing I will assign to a Feynman diagram which is like this. So there is some propagator, and the length of this propagator is related to this parameter going from 0 to epsilon. Okay. So this will be 1, 2 going to 3, 4. Okay, so the momentum flowing here is the S, right, because 1 plus 2 goes into S. And here it will be where 1 and 4 fuse together. 1, 4, 2, 3, and in 1, 4 there is the U flowing. So those are the things that you want to kind of say these words, but I have not yet said how you say them. And then this one Okay. So let me now not draw them as fat graphs. Let me just draw them as Feynman diagrams. This one will get interpreted as just a 4-point contact vertex. Okay. So SFT is a field theory that has a 3-point vertex and a 4-point vertex constructed in such a way that if you join the 3-point vertices using a propagator plus the 4-point vertex plus this other thing, then you get the full answer. So by construction, you do that. So the name of the game is to come up with Feynman rules. Okay, come up with a Feynman rule for this vertex. Propagators are obviously 1 over p square plus m square. But what are these vertices? Okay, that's the whole game. And here you have some vertex. So really, sorry, yeah.
Sorry. So the one moduli space, so to say, integral worksheet, you
chop up into these 3 things. This contribution you interpret as one Feynman diagram. This contribution you interpret as another Feynman diagram. And this is just a contact interaction. And if the moduli space is more complicated, it will be more complicated, this split. Right? So here we just had a 1D moduli space and we kind of had these 2 corners, right? So just to give an example, because it's sometimes useful to see more complicated examples, you might have a moduli space which kind of looks like a square. Okay, so this is one parameter and this is another parameter. And then you would maybe chop it up like that. I'm not drawing it right, but something like this, where there's a bulk of the thing, and then as you try to go towards a boundary, one propagator becomes long, so you're here, and then when you approach sort of a codimension 2 boundary, a second propagator becomes long. So there is this kind of tiling of moduli space as kind of recursively exposing more and more propagators in the diagram. So here I have a 4-point vertex. I can either expose this propagator, but if you had something more complicated, like a 5-point vertex, for example, if I have a 5-point vertex, you can either have this exposure, which just exposes one propagator, or you could then also have this thing, right, which would be splitting up this 4-point vertex into its constituents. So this is a higher codimension singularity. So that's the idea. Yeah.
Small comment. This is exactly the Falkenberg-Persson compact integration I was talking about yesterday.
Okay.
This is adding the extra singular piece.
Okay. I see.
Similarly there. So these are the different strata that I was mentioning.
Okay.
So you can do it in terms of binary graphs.
Okay.
So it's basically putting in the singular situation where all the particles are coalescing.
Okay.
So
Okay.
it's exactly that picture actually.
I see.
Just a comment.
Yeah. Okay. Right. So I guess this is what you would call the stratification. Like you have some codimension 1 locus in which one propagator is being exposed, and then a codimension 2 locus in which a second propagator is becoming exposed.
You have all the 5 in the same stratum. In the second
Yeah.
one, 3 and 2. There are 2 strata.
Yeah.
So that's how actually.
Okay. So now,
But do you never think of them as fixed data? Are they lower dimension objects? Or it seems like you represent them.
yeah, so you should think of them as the same dimensional object, but very thin. Yeah. So there is some canonical way in which they are associated to a lower dimensional thing, but you should really think of them as still 2-dimensional, but very thin.
I was asking if the regulator is just a tool or if it's really.
The regulator is exactly this epsilon that I wrote. So there would be some epsilon 1 and epsilon 2 in that case. Okay. So what is now the trouble, right? The trouble is the following. So you want to construct this Feynman diagram, right? And here you have a 3-point vertex. Okay. So let me draw this 3-point vertex as the following. Sorry. So let me just draw it like sometimes I like drawing Feynman diagrams like this. So this is some cubic term that you would have pulled down from the action, and these are the 3 Wick contractions that are happening. These two, this is on shell. Okay, this is on shell. But this one is generically off shell, right? Coming from this graph. This line is off shell. Okay. So just to be able to write down that Feynman graph, you need to know the 3-point vertex in string theory, where 2 legs are on shell and 1 leg is off shell. And similarly, if this 3-point vertex was appearing in some more internal graph, like maybe all 3 could be off shell. Right? For example, in this one, this is a cubic vertex. In principle, 2 are off shell and only 1 is on shell, right? So therefore, you need now a way of calculating 3-point string, some kind of amplitude or some kind of vertex in which external particles are off shell. Okay, and that is, as we know, as we are told, it's not possible to do in string theory. Okay. Okay, so then now we seem to be stuck. What should we do? Like, it seems to be that one particle has to be off shell, or at least in this simple case, just one has to be off shell. The point is that don't worry about it. Okay, don't worry about it. The idea is that if you have an off shell vertex operator and you try to calculate some correlation function, let's say, so there are some ghost insertions, but let me ignore that. There would be some V1 which is inserted at 0, there is some V2 which is inserted at 1, and there is some third vertex operator, which may be, let's say, inserted at the point 2. I don't want to insert it at infinity because it's harder to think about it. So just there are 3 points at 0, 1 and 2. These 2 are on shell. Yes?
I didn't understand how the rule for associating each of the divided integral into the diagram. How do you associate which diagram to which part?
Okay, good. So here you can think the fact that in the region 0 to epsilon, right? So x is what? X is just the position of this 2 particle. So when 2 comes close to 1, you have to do an OP expansion between 1 and 2. So this is that OP expansion, right? And similarly in this diagram, x is going close to 1, so 2 is going close to 3, right? Remember, this was at 0, this was at 1, this was at infinity. So the 2 going close to 1 is 2 going close to 3 is this. So you're doing the OPE between 2 and 3. Okay. So in this simple case, that's the idea. Now the idea is that this object is the one which is off shell, which means V3 is not a 1, 1 operator. Or a 1 operator. If it's an open string, it does not have delta equal to 1. Okay, so let's take that in quotes. It's not an operator which you normally insert. So what that means is that this correlation function as a CFT object will depend on the coordinates that you used to write your Riemann surface. Okay. So this 3-point function will depend on the choice of coordinates. And that's okay, because this off-shell 3-point vertex is not a physical observable at the end of the day, right? You are only going to put it together with this one, add all these 3 and then get a final answer. Okay, so in the intermediate steps, it's okay if the intermediate steps of a calculation depend on what exact coordinates or what exact complex coordinates you put on your Riemann surface.
Sorry, these coordinates are something between 0 and 1?
I will come to that that will be the most of the lectures, is how you pick these coordinates. So I will explain what that means.
Also one more thing, the point where you have inserted 1, 2, 3, 4
Yeah.
on the circle, can 4 go to the point 2?
That would be the other color ordering. So for 4 to approach 2, you will first have to consider a different color ordering in which is something like 1, 3, 2, 4. So if you consider them in this order, then 2 can approach 4 and 2 can approach 3.
No, but we are computing this 1, 2, 3, 4 in specific order, right? And there we'll have these two, one S channel, one U channel.
You don't have a T channel for this diagram. It's just not there. So open strings work like that. Either you consider this, or if you just want to do this color ordering, then there will be no T channel pole. Yeah.
So I thought, one point of view is that what you are constructing is a quantum field theory.
Yes.
Right, with infinitely many fields.
Yes.
And there I can certainly ask the question, what's a 3-point vertex?
Yes.
Now it could be that there is some gauge symmetry from the point of view of the field theory.
Yes. Yes.
Right, which will allow you
Yes. Yes.
So is there a way to understand this ambiguity from the point of view of space-time gauge symmetry?
Yeah, and in particular, I think Ashok has shown that it corresponds to field redefinition. So the changes of these coordinates or the changes of these epsilons are all just kind of boring changes from a QFT point of view, either some gauge transformation or some field redefinition. So the S matrix elements will be independent of all these choices at the end of the day. Okay, so the idea is that this 3-point vertex we are just using as a crutch, right, to build this Feynman graph. And then this Feynman graph, of course, by itself will depend on that epsilon. But the point is the full thing is this plus this plus this. So you see there have to be some constraints that if I change that epsilon to write what the 3-point vertex was, then this thing should correspondingly change. Right, so the couplings of my Lagrangian of this field theory are kind of have to satisfy some kind of loose consistency condition. That if you change what you meant by the 3-point vertex, then the 4-point vertex should correspondingly change so that the sum is constant. So it's important to do the split, but how you do the split doesn't matter. Right? Typically that's what happens in divergence.
And just to make sure, Raghu, you have in mind computing this bracketed object in a worldsheet calculation.
In the worldsheet calculation, yes.
After you choose suitable
Yes, exactly. So the worldsheet, is there in a very, very real way when you do SFT. It does not go away because the way you construct the SFT Lagrangian is using the worldsheet CFT. So you have not gotten rid of it at all. Like it's there, it's just incapable by itself, but SFT would be completely useless without the worldsheet. So they kind of are together. So is there a question? You can ask.
I don't understand how epsilon to 1 minus epsilon region correspond to these 3 diagrams.
No. Epsilon to 1 minus epsilon only corresponds to this diagram. So 0 to epsilon is this one. Epsilon to 1 minus epsilon is this one. And then 1 minus epsilon to 1 is this one. Okay? Okay, so now we come to how we pick these coordinates and so on. Okay. By the way, when should we stop? What is the...
So Offshell vertex operator is not necessarily 1, 1.
Exactly, no, it's not 1, 1.
So when you say 1, 1, that's the H.
H and H tilde, yeah. Right.
So
Yeah.
usually we go on till like 115 or so.
115.
115.
Okay.
Whenever you find a natural stop.
Okay, yeah. Maybe let me just explain this 3-point vertex and then we can stop. Okay.
So 1, 1 means this BRST variation of this integrated vertex operator should be vanished.
Yes, exactly. Yeah. So the another way of saying is that this, yes. Yeah, so in the people who are familiar with the BRST, it's like saying you are inserting a BRST non-closed operator here. Okay, so what do I mean by a choice of coordinates? Okay, so for that, we first have to recall the state operator map. So the worldsheet is a CFT. Okay, it has a state operator map. What is that? So for closed strings, it looks like follows. So the closed string I will represent like this. So this is sigma. It goes from 0 to 2 pi, and this is tau. This is time. So these are identified. Okay, so this is a closed string, and what you do is you make a map which is exponential of tau plus I sigma. Okay. So you do this exponential, and what you will find, it's actually easy to see, that you get the whole plane. So this locus here is this locus here. So what is happening, that at a fixed value of tau, your sigma is going from 0 to 2 pi. So when tau is fixed, the absolute value of this complex number gets fixed. So that tells you the radius of this circle. And then sigma, which is going from 0 to 2 pi, is just the angle on this surface. This point here is tau goes to minus infinity, because when tau goes to minus infinity, the absolute value goes to 0. And as you move this way, it corresponds to moving this big. And the idea is that so it's a 2D CFT, so which means the spatial manifold is one dimensional. And typically not typically, the only one dimensional manifolds which are compact are either the circle or the line segment. So this is the Hilbert space on S1. Okay, so this kind of things with various operator insertions here will correspond to the Hilbert space of the theory on an S1. And you can see that whatever operators you insert in the past will get mapped to the operator here. Okay, so the correspondence is that states on S1 correspond to local operators, okay, in the CFT. So the operator being inserted here and the state being on this unit circle, for example. Okay, that's for closed string. For open string, there is something very similar. You just work with half of this. So now your sigma goes from 0 to pi. You still have this tau. The map is the same, but now you see that sigma is only going from 0 to pi and they are no longer identified. So you will just have the upper half semicircle. Okay. So if you have a string which goes from sigma from 0 to pi, the angle is 0 here and pi here, and that's what you get. Now it's important to realize that this open string has two boundaries. So there's boundary I can call alpha and this boundary I can call beta. And typically they are different. What it means is that the worldsheet fields can have different boundary conditions on this boundary and this boundary. It's like the left endpoint and the right endpoint. And in this case, you see that this alpha boundary maps to this line, right? Sigma equal to 0.
It's the same exponential map.
It's the same, exactly the same. Yeah. So the alpha boundary gets mapped to sigma equal to 0, which is a ray, right, in this. And the sigma equal to pi, this upper boundary, is over here. So this is the beta. Okay, so you have alpha, which is a positive half line, beta, which is the negative half line, and you have this open string, which is going from one D brane to the other D brane, from that endpoint to this endpoint. So this open string is this open string, right, which has these two endpoints which are stuck on the boundaries. And in this case, you have a Hilbert space on an open interval. On a closed interval or whatever, and that Hilbert space is labeled by alpha and beta. It's very important that you have a family of Hilbert spaces, and the boundary conditions, actually, if you change the boundary conditions, the Hilbert space will change. Okay, I mean, that's just a fact of life. Okay. For a S1, it's unique because S1 has no boundary, so you don't need to specify boundary conditions. But saying that you have Hilbert space on 0, pi would be an incomplete statement unless you specify the boundary conditions on both endpoints. So the Hilbert spaces are labeled by alpha and beta. And in this Hilbert space, there's also a state operator map, which you can do insert some operators in the past, and they all will get mapped to this point here at the origin. So the states on this S1, not on S1, on the line interval, on the line segment, are prepared by some operator insertions in the past, which gets mapped to the origin. So that empty circle is where all the local operators will go for the string. Okay, so you have to think of the local operator here, and that operator prepares a state on this semicircle. So this half disk which is appearing is going to be very, very important in everything we do. Okay, so this half disk. So the half disk has a local operator at the center. It has this boundary at the bottom. Maybe we will focus on alpha equal to beta, so it will be the same boundary. And then it has this line segment stretching here. So you insert the operator here, which corresponds to a state on this thing. Okay.
If you translate this operator by some amount, it will not change the state, right?
No, it will change the state.
It will change the
Yeah.
state.
It will just add some descendants or something to the thing.
Okay.
Yes.
One more thing, if you have, instead of local operators, if you have some integrated operators,
Yes.
say, is there similar statement for state operator corresponding?
Not in any effective way that I know about. Yeah.
What do you mean by effective?
Like that's useful. Like this kind of state operator correspondence is very useful, like we will see. So, and actually there's a subtle reason why the state operator mapping is not useful in massive QFTs. Like you can say the fact that I have an operator, like let's say here, and you just do the path integral up to the unit disk, right, and define a state corresponding to an operator. But that map is not very useful, because typically how you want to use it is you want to compute some endpoint function, right? And you want to be able to use it practically, so you want to be able to replace this operator by a state. But if this operator has other insertions which are at a distance less than 1, okay, then you cannot draw just a disk around it with just that operator. And because you are not in a CFT, you cannot scale the circle. Right, so the idea of a CFT is that the state on the unit circle is related to states on smaller circles just by some trivial factor of dilatation. You cannot do that in a QFT. So,
that just time translation kind
well, yeah, this dilatation is the time translation here.
yes.
But what I'm saying is that it's important to realize that the state operator mapping, why it's discussed in a CFT. Like you could have said here that I insert the operator here and I do this path integral with a disk of some fixed radius, right? That defines a state. But in typical correlation functions, there will be operators which are closer to this operator than distance 1. Then this is meaningless, I mean this is useless. So yeah.
You should do an arrow for the alpha.
Oh no, maybe I should. Sorry. No.
So the orientation of these two boundaries are irrelevant.
No, they are not. So I will always be working in oriented string theory.
Yeah.
So this 2D graph will have an orientation.
Arrow was good.
Yeah, let's say, yeah. We have it, yeah. So I will always be working in oriented.
So, the question I asked is, in this left-hand picture, it's kind of obvious that this orientation is important.
Yes.
How do I take care of that fact there? How does the orientation come in this half-disk picture?
Well, so the orientation is just the usual the right-hand rule on the plane. So I will just do this and that's the orientation.
Yeah, but other than beta will be on the other hand.
No. So it's just this, the orientation is. Yeah. Because here it's like that. Because if you draw the orientations here, like it's backwards on this. Okay. So the idea is the following, that if you want to write down off-shell amplitudes, you think of the vertex operator as having a native birthplace. Okay, it's always born in such a unit half disk. So typically, the parent starting point of a vertex operator is here, and it's always you think of it as being inserted in some complex chart which has this unit half disk around it. Okay. For the off-shell guy. Yeah. So for on-shell guys, you don't need this because you don't need specific coordinates around on-shell operators. So for off-shell operators, you put this standard half disk around it. Okay. Okay, so what do you do? Okay, so let's say your actual arena, we were trying to calculate a 3-point function, right? Okay. So now just let's, for the sake of ease, imagine that all 3 operators are off-shell. So all 3 off-shell, because that's the most general case anyway. Okay, so we insert, so there will be a complex Z plane in which these operators are inserted at 0, at 1, and at infinity. Okay, so infinity I draw here. This is easier to draw it here. Okay. Now what do? You have these 3 operators. You imagine them as first living in their individual half disks in some separate complex planes. Okay, so 1, 2, and 3. Okay. So these are 3 identical copies of the picture that I drew there. You have an operator V1 here, you have an operator V2 here, you have an operator V3 here. You construct a conformal map from this picture into this plane. Okay. So individual, there will be 3 arrows. Okay. So what I will do is I will take this half disk and transport it to the Z plane using a specific conformal map. Okay. And that's a choice. The only thing I need here for this map, for example, is that the origin gets mapped to the origin. Let's say I'm trying to put V1 here, right? So then the map that I should do is only constrained by the fact that V1 should go to 0, okay? So let's call this coordinate W here, for example. So the map that I can write is that W equals alpha times, for example, 2Z over 2 minus Z. And let's say alpha is a large real number. Okay, so let's try to understand what this particular map is doing. So W equal to 0 gets mapped to Z equal to 0, right? What about W equal to 1? So this was W equal to 1. There is this large number here. So it will get mapped to some very small z, because this thing z will be small. So 2 minus z will be approximately equal to 2. That 2 will cancel. So W equal to 1 will approximately just be z equal to 1 over alpha. And alpha was very big. So this is something very small. Okay. So this half disk here, so let me draw it dotted, gets mapped to this little half disk here. Okay. And because this operator is not 1, 1, when you do this conformal transformation, it will transform in a certain way. Right. So when it actually lands here, so let's call this function f1. So let's call it f1 of z. In this lecture I might get the f or the f inverse wrong, but up to that, so this f circle the vertex operator at the origin. Okay, which for a primary, for example, would be df by dw to the h v1 at f of 0. So actually f is the mapping from w to z. So f is that map. So you take a particular, so you have to invert this formula. Okay. But when you do a conformal transformation of a vertex operator, which is, let's say, a primary of weight h, then it would transform by df by dw to the power h times this thing, right? So this h is non-trivial. Okay. So that means that this coefficient that you are putting in front of this operator now depends on this map. And that's what I meant by a choice of coordinates. So what you're doing is you have a Riemann surface, and you're covering it with multiple coordinate patches, with sort of one patch at least around each operator. So there's a little patch around this operator, there will be a little patch around this operator, and the patch around infinity is drawn like that. So so this is the dotted patch. This comes from the dotting. Let me draw horizontal lines here. So the horizontal lines will go here using a different f. You see, the f will have to be different because you have to map 0 to 1. Okay. And in this one, let me draw this kind of vertical. So the vertical guys will go kind of in the outside region. So that's an open set around infinity. Like if you think of it on the sphere, it's actually small open set around infinity. So there will be a map f1 here, a map f2 here, and a map f3 here. So these are 3 different conformal maps, which each map a half disk to a small half disk around the punctures. And now the operators that you have here in this arena, which is really where you're calculating the correlation function, depend on this choice of these f's. So it's also important to realize what would have happened, if these operators were BRST closed. So in the case of sort of on-shell operators, so V typically takes the form C times a matter operator of dimension 1. So the C is important now. So in this language, we will always put the ghost. So with the C, this is an operator of dimension 0. I will recall the ghosts in the next lecture, but the C ghost has dimension -1. So -1 + 1 is equal to 0. And therefore, if this thing was a primary of dimension 0, this h would be 0 and this factor would completely drop out. So in that case, this factor will not be there and you will only be putting the same vertex operator just at some other point, maybe at 0, 1 and infinity. So then you see that the choice of f1, f2, f3 is not important if all the h's were 0. But now because you're trying to have these internal legs off shell, you're forced to have these matter operators that are not of dimension 1. So it will be some, and the amount of deviation from 1 will be amount of deviation from the on shell condition. And therefore, now the f1, f2, f3 really matter. And we will declare the 3-point vertex to be this correlation function, which explicitly depends on a choice of f1, f2, f3 through, for example, this alpha. So this alpha will sit like a, like a monster in all the formulas. Like this 3-point function will depend on this alpha, even though it's a fake thing that we just introduced.
Is this a regulator kind of thing, alpha?
So alpha you don't have to pick it to be large, but you should just make sure that these things don't overlap. Because you don't want this to be so big and this to be so big that they start overlapping. So that is why I took it to be big, but that's the only thing.
Because you want their contributions to separate in the integral that you...
Not the contributions to separate, but just conceptually the state operator map works with half disks that have a single operator inside them. So if you had some, because eventually what I will want to do, I will want to cut out this part of the Riemann surface. I will want to cut out this half disk and just think of the state that is induced on this semicircle, and then glue that state using a propagator to something else. So it's important for the half disk to not overlap. Like right now we are thinking of this as a 3-point diagram, but how will you glue 2 of these 3-point diagrams into a 4-point diagram? You will take this plane, which is a 3-point vertex. There will be a second copy of the 3-point vertex, right? And 2 of the open string punctures will have to be glued. So the gluing would mean that you delete this region, you delete the corresponding region from the other guy, and then glue them on this circle. So that's why the state operator map is very important in the gluing. Okay, so you don't want to mess around with sort of individual disks overlapping in order to do that construction.
And the option guy can be anywhere, 0, 1 and...
Yeah, so that's a choice. So, okay, so that's another choice, because basically it's a choice of this function. See, in these pictures, they're always inserted at 0. When you do this transformation, it will go wherever f1 of 0 takes it. And here I just picked f1 of 0 to be 0. Yeah.
Sorry.
Yeah.
Question, but I understand why you took alpha to be large.
Yeah.
But instead of 2z over 2 minus z, I could take
put
0
anything.
over 1 minus z, anything.
You can take anything. Yeah. So yes.
How would this carry over to the 4-point thing?
So we have not discussed that yet. I will discuss it in some other context, because the 4-point thing is kind of a bit harder to do. But let me just summarize and then we can stop. So the idea is that the 3-point coefficient, let me just write. So the action will contain some coupling lambda times 3 fields, right? Phi 1, phi 2, phi 3. So if you have all of these were gluons, there will be a 3 gluon interaction with some number here. And the definition is that this lambda is equal to the vertex operators. So F1 circle V1, F2 circle V2, F3 circle V3. Where this correlation means evaluated in the CFT2. Okay. So each field has a corresponding vertex operator. You are looking for a gluon term. You take the vertex operator corresponding to the gluon, pick these conformal maps, you do this conformal transformation and take the 3-point function of those guys. Okay. So this lambda number is this number.
But are all these on shell or like?
No, off shell.
They're off shell.
They're off shell because now I use these f's, so I don't need them to be on shell anymore.
Raghu, this 1 over alpha will eventually be related to epsilon?
Yes. Exactly.
And just to understand, this is the contact diagram then in string theory.
This would be the contact 3-point diagram.
Contact 3-point.
But 3-point we only have contact. 3-point ko we cannot break it further.
You're right. But I mean, right, when you, okay, in the 4-point.
In the 4-point, there would be different. Yeah.
So is it that, because that tells you kind of the smallest tube that the particle propagates.
Yeah.
And then you say the modular space then only goes up to that point for the
4-point. Yeah.
And
So
then if it is narrower, then it's the.
yeah. So we'll do this in much, but Abhijit is preempting the case that this alpha parameter will be related to this epsilon that we had earlier.
And that's
So
why
that's
here you just did the integral over the entire worldsheet, at least in this.
Well, entire for the 3-point, there is no moduli space.
There is no modular space, but when you compute the brackets, it's just the full.
The full worldsheet path integral. Exactly, the full worldsheet path integral, no moduli. So the 3-point function is the starting point because you don't have any moduli, right? So you don't need to do any moduli integrals. So there are no divergences, IR divergences or anything. Yeah.
Yeah, so in the case of this epsilon prescription that you were telling about Witten,
Yeah.
there you have
Witten's I epsilon, sorry, yeah.
yeah, so the Witten I epsilon and this alpha are connected. Is the alpha the Witten I epsilon?
Not strictly speaking, no, they are different. Yeah.
So what was the comment that Abhijit was saying?
He was talking about the epsilon from 0 to epsilon that I was writing, that epsilon.
In your coordinate mapping, this if we put z equals to 0, it gives w equals 0.
Yes.
Epsilon gives you a finite number in w. Right? Z is epsilon.
Z is 1 over alpha will give a finite number, yeah.
But what about this point 1? If I put z equals 1, then w becomes some.
Yeah, so exactly. So you see, so you should not put z equal to 1 here because see, this was the plane that you're interested in, right? The logic is that you have these 3 punctures. So you cover your manifold with open sets. Here I'm covering it with 4 open sets. There is 1 open set here, there is a second open set here, there is a third open set which is the outside, and a 4th open set. So in this patchwork construction of manifolds, you take your manifold of interest, which is this guy. These guys are not of primary interest because this is where the 3-point function will be calculated. You take your manifold, cover it with 4 open sets, introduce local coordinates on all 4 of those open sets. The local coordinate here is the W, this W1, okay? And this W to Z map is the transition function. This map is the transition function from this open set to its sort of image in the standard, R2 or whatever. Similarly, this third one. And the 4th, you can just take it to be the unit map. So this is the 4th open set. So there the coordinate is just Z. So in some sense, what you're doing, maybe a more precise picture is the following. Thanks for this question, yeah. Yeah, so these coordinate mappings are defined locally, right? So you should not think of extending this W mapping to the whole, the thing. I mean, you can in this case because it's a PSL2R map, but in the spirit of defining things patch by patch, like you define manifolds by open sets, and those transition functions are only defined on intersections of open sets, right? So a more precise picture would actually be the following. Okay, I don't want this to, how do you stop? Okay. Some inertia, I guess. So a more precise picture of this is that you have this is your manifold, this is the upper half plane. You first take an open set, which is this, the interior of this. There's another open set which is the interior of this. And then there's a third open set which is the outside of this, and the 4th open set which is here. Now you think of so I'm going to draw the 4th open set, okay? The 3 I drew there, the 4th one I'm going to draw. Okay, so the 4th one kind of starts a little bit deeper. So this thing is the 1 over alpha point that I drew. So you see there are certain intersection regions. I'm just shading it to sort of highlight the fact that there's no colors, otherwise I would have drawn. So let's look at this like a blow up map of this region. So what's happening is you have a half disk, right? So this F1 map maps the unit half disk into this small half disk. So this is 1 over alpha, and this was like 1 here. And there is a second one open set which is starting just on the inside of it and going to the outside. You see, so there is a U1, open set U1 and an open set U2, and there's an intersection between them. So the transition function is a function from U1 intersection U2 into either the image of U1 or the image of U2, and that are those formulas that I wrote there, basically.
So conceptually, you have 4 coordinate charts.
You have 4 coordinate charts, and those 4 coordinate charts you can think of them as having these thin intersections. So you use the z coordinate in most of it, but as you start coming towards this puncture, you change coordinates to its birthplace, which was this W half disk. Okay, and you need a small overlap region in order to just do the gluing. So so that's maybe the best way to think about it. And the idea of covering each kind of insertion with its own half disk, or in the closed string puncture it would be a disk, is that you have a state operator mapping, right? So basically it's important to have this small thickness at the back of your mind, but it doesn't really matter. Like you can take it to 0. But the idea is there is some state on this thing. And then I can delete this part later, and that we'll do sort of tomorrow.
Question, could you remind how the Hilbert space labeling works with multiple operators?
How the Hilbert space labeling works with different operators. So
Multiple operators.
So you have multiple operators, but this thing here is just a line segment, right? So it's still the same Hilbert space, because the Hilbert space is only labeled by the spatial manifold. So when I cut it and I expose this semicircle, topologically it's still a line segment, which is ending on maybe some boundary. But if the boundaries are all the same, then the states on this semicircle, and this big semicircle all live in the same Hilbert space. The Hilbert space is not different. And Onkar, you had a question?
Yeah, I was wondering, since you're putting that thing up in the vertex,
Yeah.
shouldn't I be amputating the external legs or something in that 3-point function? But what I mean is that presumably if I wanted to actually calculate the 3-point function, what I would do is I would use that vertex. Right?
You will use that vertex, yeah.
So that would give me some external propagators multiplying that. Right?
No. So that does not have the propagators actually.
Oh.
You see, because that is a purely CFT object. And at that level, that is just a number.
Okay.
So if you wanted to calculate a correlation function in space-time, let's say now you wanted to calculate the correlation function phi1, phi2, phi3, right? In space-time. So you would bring that lambda vertex down. So that will be this lambda, right? And then these phi's would be external that you inserted. And then the propagators you would just add by hand. So those propagators are not part of that bracket.
That's right.
So these you will just have to add by hand.
Yeah, but then this has to reproduce the worldsheet 3-point, the standard worldsheet calculation of my 3-point function.
No. So the worldsheet actually computes the S matrix. You see, so because the worldsheet is calculating already the S matrix, these are not needed anyway. Yeah, thanks. Yeah, sorry.
Repeating my last question, could you maybe mark this alpha beta labels when you have these multiple operators, as in the boundary conditions on the upper half plane?
Yeah. So I'm just taking the same alpha. So there's alpha here, alpha here, alpha here. So for example, locally near this insertion, it just looks like the open string is stretching between a D-brane labeled by alpha and another D-brane labeled by alpha. So it belongs to some Hilbert space. But here is the same situation. Right? Now you could have
distinct alphas, it still works, or?
Yeah. But the point is, if you have distinct alphas, like let's say you had alpha, beta, gamma, then these operators will belong to the Hilbert space H alpha beta. So the set of operators that you can insert here will be different. And here you would insert operators that belong to the Hilbert space H beta gamma. Right? So that always works just by construction. So you can have different, so each operator kind of can have different boundary conditions on its two sides. But the set of allowed insertions here is precisely the ones that are allowed by the alpha beta boundary conditions. So if you have this alpha beta gamma situation, the family of operators here will be something, and the family of operators here will be something else in general. Which is just saying that these open strings live in a different Hilbert space, which can happen. But then these Hilbert spaces have a fusion rules, right? So what this is saying is that you don't just have a collection of Hilbert spaces, but there are sort of multilinear maps between H alpha beta, tensor H beta gamma into H alpha gamma, things like that. Right, that's what that 3-point function would be computing. So now it's not some 3-point function in just one Hilbert space. It's like one operator is in one Hilbert space, the second operator in the second Hilbert space. But somehow there are these multilinear maps that still make sense to calculate this 3-point function. I mean, essentially these are Chan-Payton factors, right? These are Chan-Payton factors, and we know that amplitudes have Chan-Payton factors like outside. Is that clear or?
Yeah, thank you.
Okay.
So you have
Yeah.
at these insertions you have F dot V1. So for gluons, let's say the V1s will still be the same X dot exponential IK dot X.
Yes. For the gluon, the V is like C del X mu e to the IK dot X.
But now K is not necessarily K square is 0.
Yeah, K square is not 0 necessarily. Exactly.
So you take like the same vertex of rings, but Offshell and
Yeah. No. Well, it depends on what you want to do. See, this thing K square is not necessarily 0, yes. But the transformation with F1 has nothing to do with this expression. Like I could in principle transform operators even with K square equal to 0, right, using F1. It just nothing will happen. So logically those are two different things. Yeah. The idea is, when you write down a Feynman graph, like you draw this 3 gluon vertex, you don't just write in the Lagrangian for K1, K2, K3 on shell, right? In the Lagrangian, K1, K2, K3 all are just off shell, only constrained by momentum conservation. But still there's a meaningful number that you associate with this. So in that sense, yeah, the Ki squares will typically be non-zero in this thing. And then the dependence on these F1, F2, F3s will come from this H that I raised, the Jacobian of that transformation raised to H. Okay. Yeah.
If I repeat this calculation of Sebastian with the Florence, the 4 gluon or
Yeah.
I will hopefully be able to produce dimension.
Yes, you should be. Well, the imaginary part was easy for them to get because it's related by unitarity.
Yeah.
But even the real part you should be able to do using SFT. Yeah. So one.
You said the 90 grand is real for the amplitude.
Yeah, so then you'll have to do what Abhijit was saying. You'll have to make the momenta slightly complex. You'll have to put some I epsilons and so on. That, and also the fact that when you cut these moduli spaces from 0 to epsilon, the 0 to epsilon you are not doing with the moduli space integral anyway. So that you are doing using Feynman diagram. So that is not necessarily real. Right, because the 0 to epsilon part of the integral, you are not doing it using the integral. You are doing it using Feynman diagram. So that part of my argument will break down that just everything is real now. But you will still need some, because there's a cut like Abhijit was saying, so you'll still have to have momenta being slightly complex.
Okay, so in the interest of getting some lunch,
Yeah.
let's thank Raghu.
Thanks.